In artificial intelligence, scaling context length has revolutionized large language models. However, most state-of-the-art robot policies still operate on single-step or very short history visuomotor context. This paper introduces RoboTTT, a novel robot model and training recipe that scales visuomotor context to 8,000 timesteps. This is 3 orders of magnitude beyond existing policies. By scaling context, RoboTTT unlocks entirely new capabilities, such as one-shot imitation from human videos, on-the-fly policy improvement, and robust recovery from external perturbations. To understand why long context is difficult, we must look at the limitations of current sequence models. Naively concatenating past observations introduces spurious correlations and causes robots to overfit to past actions. Furthermore, using standard transformers for long histories causes inference latency to grow with history length, making real-time control impossible. Recurrent neural networks offer constant inference costs, but struggle to compress dense, repetitive robot streams over thousands of timesteps without losing critical information. The core breakthrough of RoboTTT is the integration of test-time training, or TTT, into robot foundation models. Instead of storing history in a growing memory buffer, RoboTTT uses a sequence model where the recurrent state consists of fast weights. These weights are parameters of a small neural network that are updated via gradient descent during both training and inference. This design keeps inference cost constant regardless of context length, while providing a high-capacity parameter space to compress and retrieve long-term visuomotor histories. Training a policy over 8,000 timesteps presents severe optimization and memory challenges. RoboTTT addresses these with 2 key techniques. First, it uses sequence action forcing, which samples noise levels independently for each action chunk in a sequence to stabilize the flow matching objective. Second, it employs truncated backpropagation through time. This divides the input sequence into segments, allowing gradients to flow only within each segment while carrying the fast weights across boundaries. This keeps GPU memory usage constant. To enable on-the-fly policy improvement, the authors propose DAgger distillation. During sequence training, the model is exposed to full trajectories containing both suboptimal robot actions and human corrections. Crucially, the fast weights are updated on the entire interaction history, but the imitation loss is computed only on the human corrections. This asymmetric training teaches the fast weights to map failures to corrections. At test time, the robot can autonomously recover from its own mistakes online without human intervention. The experimental results demonstrate a clear scaling law for robot policies. As the pre-training context length scales from 128 to 8,000 timesteps, RoboTTT shows steady, non-saturating improvements in closed-loop performance. RoboTTT with an 8,000-step context outperforms its 1,000-step counterpart by 62%. On a highly complex, 10-stage assembly task lasting over 5 minutes, RoboTTT is the only method to achieve full success, while short context baselines fail completely. Beyond long-horizon tasks, RoboTTT's long context enables impressive zero-shot adaptation capabilities. By conditioning on a single video of a human demonstrating a task, RoboTTT achieves one-shot imitation on unseen configurations, succeeding in 60% of trials where baselines fail entirely. Additionally, RoboTTT exhibits high robustness to external perturbations. When a human actively interferes with the robot's progress during an episode, the policy uses its rollout history to recognize the disruption and successfully re-executes the interrupted steps. Despite its success, RoboTTT has several limitations. First, scaling training context length significantly increases pre-training costs. Future work could integrate more efficient test-time training variants to mitigate this. Second, while RoboTTT improves recovery, it does not handle every possible failure mode. Combining this approach with reinforcement learning to optimize task success directly is a promising next step. Finally, exploring more expressive architectures for the fast models could further boost performance.